back. So, today I am back with a new, important, and a trending interview question for you. And this question is very famous with the FAANG companies. And this is a single question by which interviewer can decide whether you have a depth knowledge about a system or not. So basically with this question they will judge about the knowledge. So the question is how to scale a system from 0 to 10 million plus user. So this scenario will be given to you and you have to design a system which can handle from the 0 user to 10 million plus user. So let's see how you can solve this scenario. So stay tuned, and if you like this lecture, then please hit the like button, and also you can subscribe for the futures lecture on these topics. So guys, let's start our session. So first of all, like most successful system don't start complex, right? They grow into the complexity slowly and slowly. The biggest mistake engineer make is trying to design for a massive scale on a day first or on a day one. And the smartest system begin simple. Observe the real bottleneck and involve step by step as the demand increases. So similar manner in this video, I will break down the 7 common stages a system goes through as it is scale from 0 to 10 million plus user, and each stage will be focused on the new problems that appears at the level of growth and the architecture changes that actually matters at that moment. And also we will discuss why those changes work and what they cost. So you will see when to introduce things like caching, load balancing, database, queues, and distributed system without over injuring too early. So whether you are building a real project, whether you are preparing for system design interviews, or you are trying to understand how large scale system really involve and how system works. So this is the perfect video for you. So, this process will fundamentally change how you think about a system architecture and the scaling decision. So, this is very, very important topic for you to understand. So, let's go ahead and let us start our session. So, the first stage, which I was talking among the 7 stages, is a single server stage. So, basically, in this stage we are trying to handle the user between 0 to 100. So like nowadays everyone talk about scaling to like million of user, but almost nobody tells you how system actually start. And this is very very important to know the basic, right? Because we cannot simply start by scaling for the million of user. When a new application or when a new business launches, they start with a very basic, they start with the beginning, right? So let's begin in the same manner with the simplest and the most understanding phase of a system design. So what matters at a stage, this is very important to know. When you start, just start out, okay, your goal is not to scale, your goal is to shape fast and validate your ideas. If you try to over engineer at this stage, you will not begin smart, you will be wasting time, money, or on the problems you may never face. So what's the simplest thing that works? So a single server, and this is very important stage because here we are going to use a single server. So what does a single server mean? So single server means everything run on only one machine. So what can be? For example, it can be like web application, your database, your background jobs, or sometimes even your reverse proxy, all on a same server or on a same machine. So there will be no microservice, there will be no Kubernetes, there will be no distributed system, just one machine doing all the work. So here in the diagram, you can see we have a single server. Inside the single server, web application database and the background jobs are intact. So this is the best to start your application with this design in a very initial stages. Okay, so if I will give you an example for the real world, then this is how like many successful product begins. For example, when the Instagram first launches, 10 of thousand of users signed up almost immediately. They don't build a complex system up upfront. They start simple, watch the real uses, and scale only when the system demand it. And that is the right mindset, right? And that is the right mindset, and that is very important. That when the demands comes, then only you scale your system. So now let's discuss what runs on this server, and this is important. So typically you will see a backend framework like Django, Rails Express, or Spring Boot handling the request, or it can be database like MySQL, NoSQL, or like Postgres, right? Or it can be like PostgreSQL, basically for storing the data, and the background workers handling asynchronous tasks like email, image processing, notification. So all running on a one virtual machine. And the most team use a basic cloud server from provider like AWS or like Digital Ocean. So now it is important to also discuss about the cost. So usually around $20 to $50 per month for the cost of using this cloud services and all, right? So now let's discuss. Yeah, so now let's discuss why this works so well in the early stages with a single server. Because at this stage, simplicity is your biggest advantage. Because here the deployment is easy, one server, one deploy, right? Costs are low, and also costs are like predictable, and deployment is very fast, and also debugging is simple because all the logs will be lie into the one place. So you can trace every request end to end without jumping across the services, because there will be not like, yeah, so there will be like single server, and all the logs will be captured and go into a single file. So it is easy to debug and all, right? So this actually like let you to focus on what actually matters. So what actually matters, the business logic, and also the building the features and learning from the user, right? So this is why it works so well with a single server in a very initial stage, when your user is from 0 to 100. Of course there will be some like trade-offs. So this like setup is not perfect setup, right? You are knowing accepting that there will be no fault isolation, no redundancy, and also limited scaling capacity. So that's completely fine for this stage, because this stage is a temporary stage. Now when does this stage to break? So of course there will be time comes when the user will increase, when more processing will be done to your application, then it will break. So that's fine. So you will know when the time will come to move on. Like, for example, when your database is slow down during the peak traffic, when the CPU or the memory stay above 70 to 80%, when the deployment causes visible downtime, when the background jobs crashes and affects the user request. So even a few minutes of downtime becomes an unexpectable. So at this point, one server is doing too much. So this is the moment every system reaches, and the moment where the simplicity turns into the bottleneck. And that's now when it's give you a signal to move to the next stage of scaling, right? So I hope you understand the very first stage, and this is how you have to start in the interview. You have to explain the first stage with the 0 to 100 users, when where everything will be into the single server. And then like gradually you have to say, now if the user get increase from 100 to 1,000 users, right? Then we will go to the stage 2, where we will try to separate the database. So let's say your app is working fine, users are coming in, and suddenly everything feels slow. So that is where the most system hit their first real scaling problem. Now you have to jump into the scaling, right? So like let's understand first what's going wrong here. In a simple server setup, your web application and the database share the same machine, right? That means that they compete for CPU, memory, or disk input output. One slow database query can block everything and can increase the API latency for all the users. And around 100 to 1000 users, this start to hurt, right? So now it's time to move ahead for the stage 2. And now like let's discuss the first scaling move. So the solution is simple. Move the database to a separate server. Earlier in the stage 1, we have kept the database and your like web application into the single server. But now with the stage 2, when the user increases, now we will move the database to the separate server. Now you have one server for the application and the another server for the database, right? So this is called a two-tier architecture. Here in the example, you can see that the application tier is this, where web application is there. This is the one server, and the second server is the data tier, where the database is there. So that's why it is called as a two-tier architecture, right? So let's understand now why and how this help immediately. For like separating the database give you instance benefit like resource isolation, like independent scaling, like better security and the better tuning, or like safe backup. So why I'm saying resource isolation? Because app and the database is no longer fight for CPU and memory. In stage 1, they were fighting for CPU and memory uses, but here they will not, because for every server they have their own separate CPU and memory, right? And the second point is like independent scaling. Now, if you need more RAM for the database, then you can upgrade the RAM only for the TB, right? And also it can provide better security because databases stay in a private network, not exposed to the internet. And the next point is like better tuning. So app servers optimize for CPU and database optimize for storage and input output. And also it can provide a safe backup, like backups runs without slowing down the user request, right? So this is why it is very uh, like yeah, so this is why it's give us the advantage over the stage 1. Now let's see how to manage the database services, because now we have separated the database to a different server, so we should also see how to manage those. So at this stage most team stop managing the database themselves, right? They use to manage the services with the Amazon RDS, or maybe with the Google Cloud SQL or Azure database. So these services handle the automatic backup, like security updates, like monitoring and alerting, and failover by standby servers, or like optional read replicas. Yes, they cost more, usually 50 to $100 per month extra, right? So in stage 1 the cost was little, but now with the stage 2 the cost increases, and the cost may vary from $50 to $100 per month extra, but they save hours of maintenance every week. So the time you are saving you can better spend on building the features, right? So this is how this is very important. Now let's discuss the points that when could you self-host a database, and this is also important. Self managing only makes sense sometimes if you are optimizing the cost at a massive scale. You need a very specific DB configurations, you have a strict compliance requirement, or you're building a database product itself, right? So for most team, managing database are the right choices. So there is one thing like I forgot to mention, and that is the connection pool. And this is actually the hidden upgrade. So there sometimes many people miss. Every database connection consumes memory, file descriptors, and CPU, right? Opening a new connection is expensive. and can add 50 to 100 milliseconds per request, right? So this is where the connection poolings come in. So what is connection pooling? So basically, a connection pooler keeps a smaller number of database connection open and reuse them. So you can say as a pool where the connections are present, you have to use it, and once you use it, then it will get closed, right? So for example, instead of 100 users, uh, means you for 100 users, like 100 db connections is required. So now with the connection pool you will get 100 user, but connections will get decreased from 20 to 30 actual db connections. So this is the upgrade we will get with the connection pool. So for connection pool tool like pg bouncer, so this is also an important tool which is used for the connection pooling. So it has a different pooling modes. So how it works? So it has a different pooling modes, like session pooling, transactional pooling, and statement pooling. So session pooling are safe but like least efficient, and transaction pooling are best balance for most app, and statement pooling are fastest, but you can actually like break the feature. So most system use the transaction pooling because it improve efficiently by 3 to 5x, right? So next is so what you think about the network latency? Again, this is important, right? So network latency also plays a very separate role when you separate a database. With this, it will add a network latency. So each query now add around zero point 0.1 to 1 millisecond to get a call, right? Or to finish up a call. So for most app, this is nothing, but problem only appears if your code makes 100 of DB calls per request. If the user is n plus one query pattern. So this fix is not architecture, but it is like better queries. So here you can use the batch request, use and can also use the joins and then cache for the common data. So by separating the database, you have unlocked much more scale, but now there can be new problem. Okay, your application server is the single point of failure now. So what happens when it crashes? When one server is no longer enough, so how you will handle this? So now there, so that's why the stage 3 comes into the picture, and where the stage 3 begins. So till now we discuss stage 1, stage 2. In stage 1 there will be only one server, in that we have kept the web app and database. Now in stage 2, as the user increases, we have separated the database to a different server, which is called as a two tier. Okay, and of course it has some disadvantage and the advantage, which all things we have discussed. Now your application is growing, right? Now let's say the user has become from 1000 to 10,000, means from 1k to 10k, right? And there may be chance that your server may crash. So how you will handle? So in stage 3 we are going to use the load balancer plus the horizontal scaling, right? So your app is growing, you have separated the database, but suddenly your app goes down. Why? Because you are still running on a one application server, right? One application server, one database server. So that is a single point of failure. What if that one application server get failed? Then what will happen? Just think of it, right? So the new problem just arrived. Don't panic. We will solve it together, right? So even after moving the database to a separate server, your system has a big weakness, right? Because one application server equals to single point of failure. If that server crashes, the entire application will go down, all the user will get affected, and as the traffic grows, one server simply cannot handle everything. So next step is the multiple app server. Of course, now you will increase the server from one to many. The solution is simple. You have to run multiple application server, But now the new question appears: how the user know that which server to talk on? So there where the load balancer come into the picture as a hero. So load balancer is act as a middleware where it will balance and distribute the incoming requests to the different multiple servers which we have just divided, right? Earlier we used to keep till stage 2 we have used to keep only one server, so that was fine. But now with stage 3 we have a multiple servers, right? Now there should be some component which should handle the distribution of requests to these different like multiple servers. So who will do that? So load balancer will do this, right? So let's understand first what is load balancer. So load balancer sits in front of your app server. Okay, so it sits between the client and the app server. So yeah, so something in the middle. So its job is simple: receive the incoming request from the client, distribute them across the multiple servers. Okay, and if one server goes down, so load balancer detect it using a health check. So internally, load balancer keep on checking the health of the multiple servers, who are up, who are running, who are down. So load balancer will send the traffic only to the healthier servers. Okay, it will cut off the connection with the down server, right? So from the user point of view, there will be no downtime, because user will not know that how internally the load balancer is handling, right? So if one server is down, that's fine, load balancer will not send the request to that server, it will send to the healthier server. So user will be no affected and there will be no downtime, right? So this is how we handle this situation. So how does this load balancer choose a server? Again, this is very important, and this should must know. Okay, so guys, I'm going little bit in depth, so don't worry, because this is important to understand. If you want to become a engineer and want to crack the FANG interviews, then you must know all these things, how internally these things work, right? And in the same manner you have to explain in the interview also. So let's go deep. So how the load balancer choose a server? So load balancer use simple rule, like algorithm. So basically it use a like algorithm like robin and the list connection. Okay, so common ones like round robin and the list connection. So round robin is like send request one by one to the each server, and list connection send to the server with the list active user. So basically whoever will have the list active user, so the request will go to that server. Okay, so load balancer will choose those server who have the list active like users. So this is how the list connection like yeah, so this is how the list connection algorithm works. So most teams start with a round robin because this is simpler. So if request takes different amount of time, then they move to the list connection. Okay. Now there are two places where the load balancer work. Basically, they work at a different labels. So the first label is label 4 and second is label 7. So label 4 is like load balancer. Yeah, so label 4 is like transport layer, and label 7 is application layer, basically. So layer 4 routes based on IP endpoints, and they are very fast and cannot inspect the HTTP data. But in layer 7, that is a application layer, basically, it understands the URL, headers, and cookies, and like slightly slow but far more powerful. So most web application prefer label 7 because it allows the routing for the API and the static files differently. Also, the SSL terminations is there, security checks is there, and the header based routing is there. So this is how the load balancer work internally with the algorithm, and also into the different like labels. Okay, now we will discuss the scaling approach. So there are two before adding more servers, people often ask, why not just buy a bigger server? Okay, so this is called a vertical scaling. So vertical scaling means expanding the server. Okay, so vertical scaling in that it comes upgrading the CPU or memory, so which is easy to do but very expensive. And hardwares, so there is a hardware limit. So like doubling the capacity can cost 3 to 4x times more, right? So, so this is about the vertical scaling. Now the another scaling approach is horizontal scaling. So in horizontal scaling, we add more servers basically, right? So which requires stateless application, slightly harder to implement, but gives a higher availability and fault tolerance, right? So this is how the large system scales. So there are two approaches, vertical and horizontal. So you have to decide as per your requirement and the use cases. So, and also we need to discuss important part, that is the session problem. So with the server there can be a session problem, like yeah, so this is the place where the things get little bit tricky. If a user logged in and their session is stored in a server 1 memory basically, so what happens if the next request goes to the server 2? So how the session will get to the server 2? Because for one user the session is stored in server 1 memory. So here the session is missing. User looks, so user looks like logged out. So this is called the stateful server problem. In stateful server, so this is the problem. So how to solve this? So solution is a sticky session. So basically the load balancer always send the same user to the same server, because we know that this for this user, the session or the information or the metadata is stored in server 1. So always for this user, the request will go to the server 1 only, right? So this is sticky session. So pros are that it is easy to implement and there is no code change, but of course the cons will be there. So cons are, if the server crashes, the session is lost, because the session is stored into the only one server. Okay, so if that server get crash, so session will lost. And even there will be uneven traffic, right? And it is a poor scalability. So this work for a short term but does not scale well. So now there can be a different solution, that is an external session store. So for that we use the Redis, okay, or we can use the Memcache. So any server can handle any request. Sessions are shared. Server failure does not like log out the user. So this extra latency is tiny, usually less than 1 millisecond. So this is how the most large system works, right? So at this stage, you can add more servers, you can survive the crash, you can handle the 10x more traffic than the stage 1. But a new problem is coming. Let's say a new problem is coming. No matter how many app servers you add, they all talk to the same database, because till now we have kept a single database, but we have divided the app servers to a multiple app servers. So, and but there can be problem if there will be only one database server, right? And the database is about to become your bottleneck. So that's the stage 4 which we will discuss. So in the stage 4, we will discuss the caching and the read replicas and the CDN. When the your user get increased from 10K to 100K, now your user is from 10,000 to 100,000 users, right? So everything was working fine, your app was running smoothly, there were no like bottlenecks, load balancer was working fine, and you have scaled your app servers, but suddenly everything slows down again. This time the problem is with your database. Okay, so let's understand the bottleneck first. With the 10,000 plus user, okay, almost every request still hits the same database, which is in a single server. Earlier, the database handled 100 requests per second easily in the before stages. But now, at this stage 4, your user has increased. So 1,000 requests per second, it start struggling, right? And most applications are read heavy. So there will be many reads and a very few writes in the database, or there will be many few updates in the database. So database become overloaded very quickly. So how to solve this? So big solution is to fix, we introduce the three powerful tool. First is caching, second is read replication or the read replicas, and third is CDN. So together we are going to discuss all these three, how it will reduce the database load by 90% or more. So let's break this down one by one. So first, let us start with the caching. So guys, I'm going to, yeah, so guys, I'm going in very deep. So just be with me. Okay, so like if this is very fast, then you can decrease the like the speed to a little bit slow if you want to understand more. Okay, so because I will go into a very deep now. Okay, so let's discuss the caching first. So most user, okay, so there is a simple truth that most user request the same data again and again, right? So a product page viewed 10,000 times does not need 10,000 database queries. Let's say the 10,000 users is doing the same page again and again. So like, do you think that that for the 10,000 times we need to hit the 10,000 database queries? This is where the caching helps. It is not required at all. So we can take the help of caching. Okay, so what is caching? So caching is store frequent use data in a memory. For example, database query 1 to 100 like milliseconds and cache read zero point 0.1 to 1 millisecond. So cache is more faster. If we do a database query, then it is takes like more time. But the same data, if we take it from a cache, then it will be really, really fast. So that is very fast, right? So let's understand how cache works in a simple flow. Okay, so this is the most common pattern called cache aside. Okay, so basically app check first if the cache is okay, so app checks first the cache first. If the data is found, okay, if data is there, then it will read it will return immediately, for example in zero point 0.5 milliseconds here. If it is not found in the cache, then it's do a query to a database, and then it store that result into the cache also and then return the data. This is how the it works, and this is how the future request will become super fast, because first it will check the cache. If there is no if the data is there in the cache, it will simply return it. If the data is not in the cache, then it will do the query to the db, and then that result it will also save into the cache and then return back, right? So which makes the future request also very fast. For this, like, which tool you can use for this, we can use the redis, which is most popular, and there is a memcached, which is simple and fast. So most team choose redis only because it has a supporting list. It can support set and also the leaderboard. So works for queries and counters very well, and performance is very good for the redis. So that's why most team choose redis for the caching purpose. Okay, so what should you cache? This is another question. I mean, caching is fine, but what you should cache? You should cache the product details. If you are working to the e-commerce product, then you can cache the product details, maybe the user profiles, user information, public content, or the configuration data. So bad things to cache. Now let's see the bad things to cache, like highly personalized data, frequently changing data, and large files and critical transactions data. So you should not cache these things. Okay, so this is about the caching. I hope you understand. Now the second is the read replicas. Okay, so read replicas is for sharing the database load. So even with the caching, some result still hits the database. So this is where the read replicas help. So what are read replicas? So in read replicas, one primary database handle all the writes and update request, and there will be multiple read replicas handles the read queries, because in a real application, read queries are more than the write or update queries. So like your application send write or update query to the primary database, and then they send the read queries to the replicas database. So basically we sad the database, we divide the database into one primary and multiple like replicas. So these replicas are only read queries. Okay, so this is spread the load and improve the performance. So if there will be read replicas, then of course there will be replication lag. So this is very important concept. So read replicas are usually update asynchronously. This means that replicas may be a little bit behind the primary. So for most app, this is fine. Sometimes it cause issue because if we want a real time data, then there can be problem. Otherwise, in most of the cases, it is fine. The read your writes problem is that, for example, your user updates a profile, refresh immediately, read from the replicas but sees the old data, because you have updated into the primary database, but those datas are not reflected back to the replicas database. So user may see the old data, so user thinks the update failed. So what is common? So this is the common the problem. So how to fix it? Basically read from the primary for a few seconds after write, and then use a session label consistency and then force criteria to read to the primary, right? So most modern framework handles this automatically, right? So after this problem will get solved. So this is the use of read replicas, and this will, with this we can scale our application and can handle the large number of user logged in. Now the third component we will use is CDN. So CDN means don't hit your server for static files, because if there is a static files content, like there can be images, CSS, JavaScript, videos. So these files are like rarely change, right? And are very large and very expensive to the server. So serving them from your app server is like wasteful. So that's why the CDN come into the picture. So what is CDN? Let's understand first. So CDN full form is Content Delivery Network. So this is store the static file on a server across the world. So these servers are called as edge locations. So how CDN works, let's understand. So CDN works basically, let's say if user in a Tokyo request an image. So request goes to the Tokyo CDN edge, because CDN is there in the Tokyo. If cache, then server will return it instantly. If not, then it will fetch from the origin ones. Maybe it is stored at the age of future users, right? So next request from the Tokyo is very fast, because now that static files is there in the Tokyo location. So, so what are the popular CDNs which are used by the different organizations, like the Cloudflare, like AWS CloudFront, and Akamai is also one of the famous CDN, right? So Cloudflare is especially popular due to is the free like tires. Okay, so yeah, so this is what the CDN will be helpful. So in this stage, still here in the stage 4, we have used the cache which reduce the database heat, Then we use read replicas, which scales the read queries or operations. And then we use the CDN, which remove the static load entirely. So your system can now handle steady growth. The next big challenge is the traffic spike. What happens now if the traffic get spike suddenly? So that's when we move to the stage 5. So stage 5 talks about the auto scaling and stateless design. Okay, so in this stage 5 we are going to handle the user from 100k to 500k. So at 100,000 user, scaling is no longer about growth, right? It is about survivor during the spike, because traffic is no longer predictable. Traffic can increase at any point of time. So for that, auto scaling is very, very important, right? So at this stage, the traffic comes in a wave basically. Let's say, for example, morning traffic in the USA, evening traffic in the like Europe, and a busy weekend for B2B app, weekend spike for consumer applications, marketing campaign causing 10x traffic, and a viral moment can cause 100x traffic. So manually adding server will work now. So do you think that this is impossible? Because traffic is huge, it can increase at any point of time, maybe morning, evening, night, if there is any function, if there is any festival, if there is any sale is going on. So the traffic can spike suddenly. So adding the server manually will not help at all. This is impossible. You need system that scale automatically, right? So automation is very important here. So the two big focus area at this stage, we focus on two things, that is auto scaling and stateless design. With this, we can solve the sudden traffic spike scenario. So both are required. One does not work without the other. So what is stateless architecture? This is very important, right? For auto scaling to work, server must be replaceable, right? That means no user data is stored on a server, no session in memory, no file saved locally. So server should behave like a disposal workers, basically. Okay. So when traffic increases, a new server starts, app boots up, it connect to the shared services like DB, like the Redis, etc., which we talked in the earlier stages, and then it register with a load balancer and then immediately start serving the traffic. So no manual work, no downtime. Okay. So now what happens when a server is removed? So when traffic drops, so there will, if there is a spike, then of course the drop will come in some time. So when traffic drops, the load balancer stops sending the new requested. Ongoing request get finished and server shut down gracefully. So there is no data is lost because nothing important lives on the server. So this is about the stateless design, where we are not keeping any information in the server. Okay, everything is stateless. Now let's discuss about the auto scaling. So auto scaling works by watching the matrix. For example, the common matrix can be CPU matrix. It can be CPU usage, memory usage, request count, query depth. So most teams start with a CPU based scaling because it is simpler and also reliable. So now stateless authentication with JWT is there, because at this scale many teams move from session to JWT token. So why? Because session requires Redis or DB lookup, extra network calls, more load during the spike. So JWT avoid all this, because session is requires an extra parameters, extra means extra components. So JWT is the best suited, which avoids all this. So what is JWT? Okay, let's understand this. So JWT full form is JSON Web Token. It contains user ID, roles, expiry time. And this token is signed, verified by any server, and there is no DB lookup needed. Any server can authenticate the request, right? So of course JWT has a cons, then of course they have a prawns also. So like prawns are like fully stateless, fast authentication, walk across the services. Cons are like token cannot revoke easily and slightly larger request size, because this token need to be sent with the every request. Okay. So there are common JWT patterns, like most team uses short-lived access token, and there are long-lived refresh token. So short-lived access token has a validity for 15 minutes, and a long-lived refresh token has a validity of 7 days. So this balance the security and the performance, right? So at this stage we discuss about the auto scaling and the stateless design, right? So at this point, like servers scale automatically now. You don't need to add the servers like manually when the traffic gets spiked suddenly, right? And if the spikes are down, then it will gracefully, it will lower the servers, right? So traffic spikes are handled smoothly, failures are absorbed automatically, and application trial is elastic. So your system breathes with the traffic. But now new limit appears, right? Database write limits, maybe the monolithic become harder to change. Some tasks are too slow to run synchronously. So where the stage 6 come into the picture. So let's move to the stage 6, where we will discuss the asynchronous processing. We will discuss the queue and the service decomposition, and where the that will really get interesting. Okay, so in stage 6, let's say the user will become 500,000 to 1 million. Now we have reached till 1 million, and with this system design we can handle the 1 million users. So at half a million users, scaling stop being about tuning. Now it is about changing the shape of your system, right? Because the old tricks are no longer enough. So at 50,000 plus users, you start hitting a hard limit. Basically, the database cannot handle all the writes anymore, right? Deploying a small feature takes forever. Same requests start taking seconds. One part of the app need 10x more scale than other. This is where the advanced architecture begins. So basically the three big tools at this stage. First is database sharding. Second is microservices. Third is messaging queue for asynchronous processing. So let's understand them one by one in a very depth manner. So first we will discuss database sharding. So basically the read replicas help with the reads, but all the write still goes to the one database, that is a primary database. At this scale, the single database become the bottleneck. So with this, we have to do the sharding. So sharding means splitting the data across multiple databases. So there is a one database, we split the data into the multiple databases. And for write, there will be only primary database, and for read, we will do from the separated databases. So each database handles its own subset of data. Each shard handles both reads and write. Okay, for example user from 1 to 1 million will use the shard 1, and user from 1 million to 2 million will use the shard 2. So now the writes are separate across the machines. Okay, so sharding is actually a one way decision. Means, I mean, once you shared, the cross shared queries become difficult, transaction across shares are complex, migration must run on every shard, and application logic become more complex. So that's why you delay the sharding as long possible. Earlier we have not discussed the sharding because this is very complex process, but now when the user has reached till 500,000, then we are discussing to the sharding. So in the similar manner, you don't have to discuss this sharding thing into the into the very earlier stages of your system design in the interview. You have to go step by step, and you have to means tell that if the user increase, if the scenario will come, then you will discuss the starting. So that's why we have delayed this discussion and now we are discussing, right? So when should you start? This is important. Only start when you are a right bound. One database physically can't keep up. Your data sets does not fit on one machine. So before starting, always try the better. So there are some steps we should means keep on doing before starting. If those didn't work for you, then go for a start. So what are those steps? The steps are like better do first indexing. Better you can do the query optimization. Maybe you can use the caching, read replicas, and the bigger machines. If those didn't work and there is no option left, then go for a sort. Okay, so this is about the sorting. Now let's discuss the microservice. Microservice is like breaking the monolithic into the independent services. As the team grows, the monolithic become painful, right? Signs up, you need microservices. So smaller changes require full redeploy. Teams block each other. Different features need different scaling. One bug crash everywhere. So so hero is microservice for this scenario. So what is microservice? So microservice is basically splits the app into the independent services, and each service will have your own its own data, deploy independently, and then scale independently, and also use the best technology for its job. For example, the services in the e-commerce project, like search service, notification service, order service, payment service. So all these services are uh, developed as a separate microservice, which has its own data, which will deploy independently, which will scale independently if required, and which will can use any other technologies to build on, right? So important rule is don't split everything at once. Best approach: extract one service at a time. Start with the cleanest boundary and avoid like creating dozen of services upfront. Go slow by slow, one step one. So services add okay, so microservices add the flexity, but it also brings the complexity, and this is important, right? So yes, so microservice will help in case your team grows and all. Now, next topic is messaging queue. Basically, this is help for asynchronous processing. So, at this scale, doing everything synchronously is too slow, right? Because not everything need to happen before responding to the user. So, there is a concept of synchronous versus asynchronous. So, when the user places an order, so must happen in like immediately is like it should first validate the payment, then check the inventory, then creates the order, and then return the confirmation. So what things can happen like later, that there can be send email, send update analytics, maybe the notification, maybe update recommendations. So these things can be done later. Okay, so where you can use asynchronous process, and the certain things like validating payment, check inventory, creates order. So these can be used as a synchronous, right? So now how message queue will help in this scenario? So message queues are queues like Kafka, a Rabbit queue, SQS, allow services to come to communicate asynchronously. Okay, so instead of calling services directly, you publish an event and the other services consume it when it is ready or when it is required. So benefit of messaging queue is like resilience, scalability, decoupling, spike handling, retries. And this is the pattern where you do the right now and do the heavy work later. Okay. And this is very important. So messaging queue help in asynchronous processing. So If I talk about the real world example, so in social application, creating a post is instance, but feed update, notification, indexing happens later. That's why likes appear slightly delay, feeds update gradually. So this is asynchronous processing at the work, right? So all these things are happening with the messaging queue. It can be any tool like Kafka, RabbitQueue, or SQS. But the functionality is this. That's why we see little bit delay. Okay. So at this stage, write scales horizontally, team ship independently, slow works asynchronously, system handle massive traffic. But next, there is again one problem arrived. Your user are no longer in one place, right? Then how you will handle? The user are in different countries, continent, different latencies. One data center become risky. That's where we move to the stage 7, and stage 7, multiple multi-reason plus advanced pattern we will see, right? Where your users are globally. So global scale and multiple reason architecture is required. And till here, your user become 1 million to 10 million plus. When your app reaches million of users, scale is no longer about servers. It is about geography. So what break at the global scale? At this stage, your user are everywhere. And new problem appears. User in Australia wait 300 millisecond to reach US server. One data center outage can take down the entire application. One database schema cannot handle both real-time updates and the analytics. And different countries have their different data laws. So your system must now think globally, right? Because your application has been used from the global. So what can be the solution for this? At this level, we introduce the multi-region, advanced caching, and specialized pattern like CQRS. So we will discuss one by one, so don't worry. So multi-region means like running your application in multiple geographical location. Why this is important? Because there are two main reasons. First is lower latency. For example, okay, first is lower latency and second is higher availability. For like lower latency, for example, let's say user connect to nearby server from Tokyo to Tokyo in 20 milliseconds. If the user is not in Tokyo and then connecting to US, then it takes 200 milliseconds. So there will be lower latency, right? And for higher availability, if one region goes down, so other keep working. So this is the true disaster recovery. So low latency and high availability. So the two common multi-region models. So multi-region models are like active passive, which is primary secondary, and then another is active active. Okay. So first we will discuss the active passive. So in active passive, that is primary secondary. One region handle all the writes, other region handle the reads. If the primary fails, then secondary take over. So pros are like easier to build, strong consistency, and no write conflicts. So of course, if there is a pros, then there will be cons also. So cons are like slower writes for far away user, which are very far, and failover takes time, right? So most companies start here. Now the second part is active active. In this, all region handles reads and write. Okay, user writes data locally. So this sound great, but it is very hard. Pros wise, like lowest latency everywhere, no single point of failure. And cons are like conflict resolution in complex data become eventually consistency, and debugging is very difficult in this. So active active requires serious distribution system expertise to handle. Okay. So this is about the active active and the active passive architecture for multi region. Now I hope you have heard the term cap theorem. right? So at global scale, the cap theorem stop being theory. You can only choose two things at a time. Either you can go with the consistency or availability, or availability or partition, or partition or consistency, right? So consistency means everyone sees the latest data. Availability means system become response, and partition tolerance means survive network failure. So network partitions will happen. So during failure, you choose consistency or availability. So it depend on your use cases, how you are using the cap theorem, right? So most global system choose availability. That means post may appear second late, but profile updates take time to sync up. Rating may differ briefly by region. This is called eventual consistency. In distributor system, there is a no yeah, so there is, what is that called term, yeah, so only there is a eventually consistency, right? So there is no urgent consistency or active consistency, I will say. So only critical operations like payment, inventory, or financial data have a very strong consistency and may route to a primary reasons. Okay, now let's discuss the CQRS pattern. So as the system grow, reads and writes looks very different. Write need transactions, validation, strong consistency. Read need speed, aggression, and search. So CQRS pattern separates them. So how CQRS pattern work? So write send, which are clean and normalized data. Read side is very fast and like denormalized data or view, and event keep them in sync. So that's why feed update smoothly even at a huge scale. So there we use the CQRS pattern. All right. So now next is advanced caching at a global scale. So caching also evolved, right? Multi-tier caching is there. I mean, in the browser cache, CDN, app cache, database, each layer reduce the load and latencies. All these things we use as the system grows, right? So caching, so caching is again to the multi layers and multiple things which are important. So at this stage, in the stage 7, there is no perfect system, right? We come to know. With the stage 7, we have discussed everything, and we discussed that there is a no perfect system. Only trade offs like consistency versus availability, simplicity versus power, cost versus performance. So that is what real system design it all about. I mean, you need to decide that which thing you choose, and with that, as per your scenario, as per your situation, you have to design your system, right? So this is the total stage 7 we discuss. Now beyond 10 million user, that is extreme scale architecture. Once your system crosses the 10 million user, you are no longer just scaling, you are inventing. At this level, many of the self tools start to break down, and the companies begin building custom infrastructure. So the predefined infrastructure will not work. You have to go with a very expertise people to design a custom infrastructure. Why is scaling hard get hard after 10 million user? This thing you should know. At extreme scale, your traffic patterns become very unique. One database cannot handle everything well. Latency expectations are extremely strict. Small inefficiency turns into huge cost. The problem are no longer generic. They are specific to your product, right? So that's why it is very extreme scale architecture we need to use. So why company build a custom system? Sometimes even the right database is not enough, right? I mean, at a massive scale, some companies build custom system because existing tools cannot meet their need. For example, Facebook Tau, right, built to handle social graph with extremely low latency. And then we have a tool or system like the global spanner, which is used for a globally distributing SQL database with a strong consistency. There is a Netflix EV cache, a custom caching system that built on the top of the MAM cache, because MAM cache was not sufficient to handle your requirement. So Netflix has built the custom cache system. In the similar manner, Uber schemeless. Okay, so in this MySQL based system designed to scale transactions beyond a single database. So these system does not exist in a one day or into the first day, right? They were built only after scale demands it. So scaling is not a destination, right? The architecture that work at 1 million user will almost never work at 100 million users. So you have to involve as the user get increase, and there may be chance that you have to add a custom design. So that is what the product company do. They they build the component as per the use case or the requirement. So system involve consistently, right? Okay, so I think I have covered everything, but okay, we have some things more I have added for you how to choose the DB choices, so you can take the screenshot or pause and read it. So this is a some scenario like if the data type is transactional, then you can go with the Postgres, SQL, MySQL, or Cockroach DB. So why you have to choose this? Because it is an acid guarantee property, familiar SQL, and mature tooling. So the reason for adding this to table, so this will be helpful for your in the interview basically. So which database you have to choose at which scenario. So just have a look, or also you can take a note. So this will be helpful. If you get these scenarios, then you can use the database as per the choice. And further, okay, so let's wrap up. So at a massive scale, you stop copying the architecture, you start designing your own workload, right? Every decision is a trade-off between the cost, latency, and the complexity and the availability. And the biggest lesson to all is scale only when the problem force you to. Too early, waste money; too late, cause the outage, right? So summary is that if the user is 0 to 100, go with a single user, everything together. Benefit is save fast, validate idea. When the user is 100 to 1K, separate database from the app server, which is called as a two tier, right? And when your user is 1K to 10K, then you can introduce a load balancer, horizontal scaling, and vertical scaling and all, right? And when the 10K to 100K, when the traffic spikes, then go with the caching, read replicas, or CDN. When your user is 100,000 to 500,000, then you can go with the auto scaling and external states to handle the spike traffic automatically. And when your user is becomes 500,000 to 1 million, then you can go with the sarding. And before sarding, just take the different approaches which I have explained, like indexing, like the query optimization. If those not help, then go with the sarding, and then go with a microservice approach, or maybe the messaging queue, that is asynchronous processing. Okay. And then if your user is 1 million to 10 million plus, then of course multi reason approaches will be you have to use, because now your user is global. And you can use CQRS patterns and specialized store. Maybe you have to create your custom cache and other things, because benefit is global performance and disaster recovery. So this is the overall summary in a one table. And I hope you get a very crystal idea about the system design, how you can think of a stage by stage, part by part, and this will, yeah. So I think if this